Hi everyone. So today I'm going to be going over the November 2018 paper for grade 12s. This is paper 2, so chemistry. And yeah, I'm going to start. This first section is going to include questions 1 to 5, and the second question or the second video will include questions 6 to 10. So I'm just going to jump right into it with a multiple choice. I'm going to start with question 1. So question 1.1 says, write which one of the following is the structural formula of the functional group of the ketones? So something that's very important to know is that with chemistry, the more you study, the better you'll do. So you need to basically study the names of functional groups, the structures of the functional groups, how to name them, all those kinds of things. So that information should be in textbooks, but that's the kind of stuff you need to know off by heart to answer these questions. This is not something that you can figure out during the exam. And so this is just knowledge that you have to have before you walk into your exam. So you need to know this table, and then you can basically have a look at each one of these options and you can say, okay, well, which one is a ketone? So you can obviously see that A kind of follows a similar structure to what a ketone looks like. But the reason it's wrong is because it doesn't specify that the carbon in the middle is bonded to two other carbons. The lack of clarity on what the additional things this carbon is bonded to eliminates it as an option. Okay, then option number 2 kind of follows the structure as seen over here, which is an aldehyde, not a ketone, so you can eliminate this one. And D is very much in alignment with an alcohol, if you have a look at the structure over here. And so that means that our final option has to be C. And you can see that from this diagram, it specifies that it's bonded to a carbon on either side, as it does in your functional group structure. Okay, so the answer for this one is C. That's the functional group of a ketone. Okay, and then 1.2, which one of the formula below represents an alkane? So this one seems a little bit more difficult because you kind of think to yourself, oh, do I have to draw every single one of these now to figure out where the double bonds are? But this question becomes a lot easier when you, number one, know what an alkane is. So you know that an alkane is a hydrocarbon that only has single bonds, okay? Alkene has got a double bond, alkyne has got a triple bond. So you know that what you're looking for is a formula that has no double bonds and no triple bonds, only single bonds, which means that every carbon is going to have the maximum amount of hydrogens that it possibly can, okay? And you know that the general formula for an alkane is carbon, the number of carbon, if the number of carbons is N, then it means that the number of hydrogens that your carbon has to have in order for it to be an alkane is 2N plus 2. So your ratio number for your hydrogen has to be the number of carbons you have multiplied by 2 plus 2. This is a general formula for an alkane. So all you really have to do is find the option that follows this general formula. Okay, so let's answer this question, and then I'll also just point out what the general formulas are for alkenes and alkynes, because obviously in exams they can ask you for any one, and this is a much easier question if you know the general formulas. So first things first, A says C2H4, okay? So if there are 2 carbons, if it was an alkane, it would have to be 2 times 2 plus 2, which would be 2 times 2, which is 4, plus 2, which is 6. So it would have to be C2H6. So definitely not A. A looks more like an alkene to me with a double bond. So we can eliminate A. Okay. B, we've got C5H10. So we take our number for carbon, as our n, which is 5, and we say 2 times 5 plus 2. 2 times 5 is 10, plus 2 is 12. So if it was an alkane, I would need 5 carbons and 12 hydrogens, and I only have 10. So there's definitely not only single bonds happening here. There's somewhere where there's either a double or a triple. So you can eliminate B. Then we have a look at C. So we see that the number of carbons we have is 14. And if N is 14, 2 times 14 is 28, plus 2 is 30. So that means that C is our C is our alkane because it follows the general formula for an alkane. Okay, and we can just double check D. You'll see if N is our C number, then 2 times 8 gives me 16 plus 2 gives me 18. And we're kind of short on hydrogens there. So this general formula makes it much easier. I do just want to quickly write the general formulas for alkenes and alkynes. Like I said, if you have another exam and they're asking for an alkene or an alkyne instead, it will help to have these general formulas memorized. So the general formula for an alkene is CnH2n. So whatever the number of carbons you have in an alkene, you need to have double the amount of hydrogens. And that's why I said A kind of follows that structure, because we've got 2 carbons and double the amount of hydrogens. So that's definitely an alkene. Okay? And then our general formula for an alkyne is CnH2n minus 2. Okay? So we can have a look at D, for example. If 8 is the number of carbons we have, then we say, okay, well, 8 times 2 gives me 16 minus 2 is 14. So we can with confidence say that D follows the structure of our alkyne general formula and can therefore fall under that category. So might just be a good idea to write these down, have them in the back of your mind, makes answering these much easier. Okay. Yeah, so our answer for 1.2 was C. Now we move on to 1.3. So consider the organic compound below. The IUPAC compound, or name of this compound is. So this is a pretty simple one. It's an alkane, nothing too stressful. So the first thing you have to pay attention to is when your carbons in the main chain, so this is your main chain here, are not bonded just to hydrogens. The CH3 and the CH3 are going to be considered branches on your main chain. This is your main chain. These 4 carbons in the middle here, this is your main chain. So these are branches. So when you're naming according to IUPAC rules, the numbers that you put at the beginning of your name to describe the position of your branches, so these are your branches, needs to be the lowest number possible. So if you're unsure to know which side do you start counting from, do I start counting 1, 2, 3, 4, or do I start counting 1, 2, 3, 4 in terms of giving a number to the position of these chains? You need to choose the direction that will give the number at the front the lowest possible number. And that means that we're going to have to start counting from our right-hand side. So we count 1, 2, 3, 4. Now we can have a look here. You can see these are also something you need to memorize in terms of naming. Like I said, chemistry is a lot of study work. The more you study, the better you do. So we can see the number of carbon atoms, and the prefix that aligns with this is but. So we know that our prefix is definitely but. Okay, we know that it's an alkane. So you know that the suffix must be ane. Okay, and as I said, you start counting from the side that will give your chains the lowest number at the front, which is going to be 1, 2, and we've got 2 chains. So you say 2, 2, and our chains consist of 1 carbon, which means their prefix is going to be meth, and it's going to be, because there's 2 of them, we use another prefix of di, and di means two. So we say 2,2-dimethylbutane. So the 2,2 tells me where my dimethyl chains are. This dimethyl describes the nature of the chains. The 2,2 tells me where these two chains are, and the butane tells me how many carbons are in my main chain, and it tells me to which functional group this compound belongs. So from this, we can therefore deduce that our answer to 1.3 is C, 2,2-dimethylbutane. Okay. Now we move on to 1.4. So the question says, activation energy can best be described as the minimum energy required to A, cause effective collisions, B, make reactant molecules collide, C, change the orientation of reactant molecules, or D, increase the kinetic energy of reactant molecules. Okay, now if you know the official definition of activation energy, this one should be easy for you. Okay, uh, activation energy is the minimum energy required to cause effective collisions. It's immediately A. Okay, because if you knew the definition, that would immediately be your first choice. And then just to elaborate a little bit further, effective collision means that molecules or atoms within the reaction vessel are able to collide with sufficient amounts of energy in the proper orientation, which will facilitate a reaction. So facilitate a reaction occurring. So 1.4 is A. Okay. 1.5, which statement is correct for a system in dynamic equilibrium? Okay. Well, the word dynamic tells us that it's changing or moving. Dynamic means it's not staying the same. Static, on the other hand, means the same. So when we're referring to dynamic equilibrium, it means that we're looking at a reaction that goes both ways. It means that it's got reaction arrows moving to the left and to the right. Okay, it's not a one-way reaction. It's not a reaction that runs to completion like a normal reaction. Okay, so which one of the statements is correct? A, all reactants are used up. You can immediately eliminate that because all reactants are used up only in a one-way reaction. So in a reaction only runs to completion if reactants are in the correct ratios and if it's a one-way reaction. So you can immediately eliminate that one. B, the forward reaction is equal to the reverse reaction. So you almost feel tempted to choose that one, but it's not true. The true statement would be the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, so you can eliminate that one. It's not completely true. Okay, C, all substances in the reaction are of equal concentration. Also not true. You don't necessarily start a reaction with the same amount of reactants and products. And when your system reaches equilibrium, it doesn't necessarily mean that everything is in an equal concentration. Okay, so your best choice at this point is option D, because you've already eliminated the first three. And D says the concentration of the reactants and the products remains constant. Okay, and this is true. Unless disturbed by some kind of external force that's like a change in temperature, a change in concentration, like a researcher manipulated change in concentration. So D is the answer for this one. Okay, then we move on to 1.6. Initially, a certain amount of P gas was placed in an empty container. A hypothetical reaction reaches equilibrium in a closed container according to the following balanced equation. Okay, and it says at time t, the temperature is increased. Which graph below best describes the resulting changes in rates of the forward and reverse reactions after the temperature is increased? So the first thing I want to discuss before we answer this is basically telling you that your change in enthalpy or change in heat rather is smaller than zero, which means it's a negative number. And a negative change in H indicates that the forward reaction is exothermic. Okay? Additionally, they said that the temperature is increased, and an increase in temperature favors the endothermic reaction. So that means that because our forward reaction is exothermic and they're increasing the temperature, and an increase in temperature favors endothermic, it means the reverse reaction is going to be favored. Okay? So we have a look at the graphs. Pretty much they all stay at the same place, but you've got the reaction rate of the forward and the reaction rate of the reverse. A spike in temperature is going to cause the reaction rate of both of your reactions, both forward and reverse, to dramatically increase, because if the reverse reaction is favored, it still means that something is happening on the other side of the equation. Okay, there should be examples of these in your textbook. Very difficult to just identify out of nowhere, so I would say go and familiarize yourself with these graphs from your textbook, from online sources. Go and do some research on what these changes look like on a reaction rate graph. And this will kind of give you more insight as to why B is correct. Okay, it's basically because temperature causes a spike in both of them before a new equilibrium is kind of established. Okay. Okay, 1.7, reactions 1 and 2 below have equilibrium constants, Kc greater than 1. Based on the reactions above, the acids in order of increasing strength, so from weakest to strongest, are. Okay, so all you basically got to do with this question is identify in which reactions each compound which compound is acting as an acid. So you know that according to Bronsted-Lowry's theory, that an acid is something that donates. So you can see here your acid, it donates a proton. So you can see HCl has donated its proton to H2O so that H2O can become H3O positive. Okay, and a base accepts a proton. Okay, in this scenario, the proton is an H positive ion. Okay, and yeah, so that's how you identify which one is acting as the acid and which one is acting as a base in the reactions. So we go and we have a look at the first one and we say to ourselves, okay, well, H3X, when reacting with HCO3 negative, is in fact donating. It's donating an H, because can you see it goes from being H3X to being H2X minus. It's become negative because it's lost an H, or in other words, a proton. And you can see that HCO3 negative has gained a proton, which means that in this reaction, H3X is acting as the acid. Okay? And that tells us that H3X has stronger acidic properties than H2CO3. Okay, so you already know now that H2CO3 is weaker than H3X. Okay, next step is we say, okay, well, now we've got H3O positive and H2X negative reacting in the same reaction. Okay, and we can see in this scenario that H3O positive is acting as the acid because it has donated an H positive or a proton to H2X negative to give H3X, which means that in this reaction, H2X negative is the base. It has accepted the H positive, which means that when in a reaction vessel, H3O positive is the stronger acid, okay? Which means that H3X is weaker than H3O positive. And then what they want is they want the acids in order of increasing strength, so from weakest to strongest, and that's what we've just done. H2CO3 is a weaker acid than H3X, and H3X is a weaker acid than H3O positive. So now we're just looking for the option that puts them in this order, and that's going to be okay. Cool. Now we move on to 1.8. It says, consider the cell notation for a galvanic cell. Okay. Which one of the following half reactions takes place at the anode of a cell? Okay. Well, important to remember that our summary or our notes tell us that oxidation occurs at the anode and reduction occurs at the cathode, okay? And oxidation is the loss of an electron. So they want to know what's happening at the anode. You know that anode oxidation occurs. So you know that whatever's happening at the anode needs to support the loss of electrons. So your atom or your ion needs to become more positive. If something's happened to it at the anode, it's losing electrons, which means it has to become more positive. Okay? Because it's losing electrons. A loss of negative charge means you're becoming more positive. Okay? So we have a look and we say, okay, well, Ni or nickel as a solid undergoes a reaction to become Ni2 positive. So it started off neutral here, and in order for it to become 2 positive, it has to lose some negative charge, so it loses 2 electrons. On the other side over here, we have an H positive ion, a positive ion becoming neutral, which means in order for it to move from positive to neutral, it has to gain some kind of electron, some kind of negative charge. So you know it's definitely not the H. We're definitely not focusing on H here because H is undergoing reduction. It is gaining electrons. It's becoming more negative. It's losing positive charge and becoming neutral. So it means that nickel has to be the answer. So you can immediately eliminate A and B because we're not looking at H. And now you just need to write it in the correct order. Okay, now you need to choose between C and D. Remember, oxidation is the process of losing electrons. So if we look at C, here we've got Ni2 positive gaining 2 electrons to become Ni. So this is not correct. This is reduction. This is your reduction half cell reaction because if you started with Ni2 positive and it gained 2 electrons, it would be gaining negativity. It would be gaining electrons and be undergoing reduction. So you know that your answer has to be D because it has to be the version of the half cell that causes Ni to become more positive through the loss of electrons. Okay. 1.9. Which one of the following is applicable to an electrolytic cell? Okay, so let's have a look. A, reduction takes place at the anode. That's wrong. Oxidation takes place there. Okay. Oxidation takes place at the cathode. Also wrong. Okay, we know that reduction takes place at the cathode. Okay, C, it uses alternating current. This is a physics concept, not a chemistry concept, so we can just cut it out, okay? But here I've given you an image of an electrolytic cell. So remember, there's a big difference between a galvanic cell and an electrolytic cell. And so D has to be the answer for 1.9, because as you can see from the image, we've got a battery happening here, and the battery is used for the cell to function. Okay, and again, just a summary: cathode reduction happens, anode oxidation happens. Okay, perfect. Now we move on to 1.10. So the flow diagram below shows 4 stages, A, B, C, and D, in the conversion of sulfur to sulfuric acid. And they want to know, at which stage is a catalyst used? So this information, I think it's in one of the, I'm not sure which chapter of your book, either the chemical industry or like fertilizers, but I think it'll be in the chemical industry side of things. And there are a few of them that you have to learn. This is one of them. One of the others is the production of fertilizers. So chemical industries used in the production of fertilizers. So these you have to know. You have to study them. Like I said, chemistry is a lot of study work. And basically, I've put an image alongside here, and it's basically showing you, okay, we start with this, stage A, we move to sulfur dioxide, and stage B, and you can see exactly that it says that oxygen is needed as a catalyst at stage B. So I'm choosing B. Okay, again, this is something you would never know unless you studied. It's not stuff that you can figure out in the middle of the exam. So go have a look at all of your theoretical work, because the theoretical work is very, very important in chemistry. Okay, let's move on to our next question. Question 2. Okay, question 2 says a test tube containing a straight chain organic acid X, ethanol, and a catalyst is heated in a water bath, as illustrated below. Okay, so they give you the little diagram that you can see there, and they say that organic compound Y is produced according to the following equation. So give a reason why the test tube is heated in a water bath instead of directly over the flame. Okay, so the first thing I want to point out is that you can see that the test tube contains an alcohol. Okay, and one of the very important properties of an alcohol is that they are flammable and they catch fire easily. So you obviously don't want to be exposing ethanol to an open or direct flame. And so the reason that you're putting your ethanol in a test tube and heating it over a water bath is so that you don't cause an explosion, or you don't cause the contents of your test tube to catch fire after being exposed to a direct flame. It's basically a safety measure to make sure that everything is heated evenly and alcohol isn't evaporated, and to make sure that the volatile nature of ethanol doesn't cause a fire or an explosion. Okay, cool. 2.2, write down the 2.2.1, the type of reaction that takes place here. Okay, so if we have a look, we have got compound X plus an alcohol giving us compound Y with water. Okay, and you can see that a catalyst is used in the description, and you can see that heating is required to facilitate this reaction. So again, you're going to have a very detailed, or you should have very detailed notes on the reactions that occur in organic chemistry. And if you've studied those well, and you know what the reaction conditions are, and you know what catalysts are need to be used where, then you will know that this is a condensation esterification reaction. Okay, you just have to be able to identify the components, the reaction conditions. So the reaction conditions are going to be like heat and a catalyst, for example. Okay, this is also a very common reaction that is set up as an experiment in class. I don't know if any of you have done it, but just know that this is a common setup for an esterification reaction. Like I said, many of them I can't explain. You just have to go back to your notes and study as hard as you can. These are the types of things you have to identify. Okay, so 2.2.2, name the formula of the catalyst needed. And once again, if you've studied your reactions from your notes and your books, you'll know that one of the reaction conditions for esterification is a catalyst, and the formula of that catalyst is H2SO4. Again, this is not logical stuff. This is stuff you have to study. Okay. 2.2.3, homologous series to which compound Y belongs. Okay. So when an ester is being formed, okay, yeah, the homologous series. Sorry, I'm getting a bit off track here. So the homologous series, again, that's going to be something that you have to study. And the answer is esters. So you need to study functional groups, homologous series, and the suffixes for IUPAC naming. Those are all things you have to have in your mind. Okay, I'm just going to write esterification here for this answer, just in case you are unsure. That's for 2.2.1. Okay, then the molecular mass of compound Y is 144 grams per mole, and its empirical formula is C4H8O. So 2.3 says determine the molecular formula of compound Y. Okay, so just a reminder that esterification uses a carboxylic acid and an alcohol to form an ester that has both a fragment of acid and a fragment of alcohol. Okay, so the first thing that we want to look at is how do we calculate a molecular formula from an empirical formula. So you need to remember an empirical formula is the ratios of each of your atoms in their simplest form. So the ratios have been simplified. So you don't actually know how many of carbons to hydrogens and oxygens you have in the real molecular formula. You just know what the ratio is of each of the atoms. Okay? And so the way that we do this is they've said that the molecular mass of the actual compound is 144 grams per mole. So we fill out our formula, okay? We say the molecular mass of our real compound over the molecular mass of our empirical compound. That's going to give us a ratio. So we're going to substitute in the 144 grams per mole for the molecular mass of the real compound, because that's what they gave us. And now we have to go and calculate the molecular mass of the empirical compound. Okay? And the empirical compound molecular mass, you're going to have to go to your periodic table, okay? And you're going to have to get your approximate relative atomic masses of carbon, hydrogen, and oxygen off of your periodic table and multiply them by the numbers that they have in front of them in their empirical formula. Okay? So it's going to be the empirical formula of carbon, which is 12, the relative atomic mass of carbon, which is 12, plus that of hydrogen, which is 1, plus that of oxygen, which is 16. Okay. And now you need to just go back and remember to multiply each of your relative atomic masses by the number of atoms that you have in your empirical formula. So it's going to be 4 times 12, 1 times 8, because we've got 4 carbons, we've got 8 hydrogens, and we've only got 1 oxygen. So that becomes 144 over 72. Remember I said the 16, 1 and 12 are numbers that I got off of the periodic table. It's the approximate relative atomic mass of each of these atoms directly from the periodic table, okay? And then we divide those two. So we say 144 divided by 72, and that gives us 2. So that's the ratio we're working with. So our ratio of molecular mass for real compound to molecular mass of empirical compound is 1 to 2. Okay? And so now what we need to go do to get our molecular formula is to multiply each of these ratio numbers that they've given us for the empirical formula by the ratio number we've just calculated. So you're going to say C4H8O, which is our empirical formula. You're going to multiply all of your ratio numbers by 2, and that's going to give you your molecular formula. So it's going to be 4 times 2 is 8. 8 times 2 is 16. And 1 times 2 is 2. And that is your molecular formula. C8H16O2. Okay. The next question says, write down the IUPAC name of compound Y. So you obviously know that compound Y is going to be an ester, okay? And you know that you are combining an alcohol that has got 2 carbons, okay? Which means that its prefix is going to be ethanoate, okay? Ethanol, which they've already given you. And they've told you how many carbons are going to be in your final Y, which is 8, okay? And you know 2 of those carbons have to belong to the alcohol, because remember, when you're naming it, a portion is used to name the alcohol that was used, and a portion is used to name the carboxylic acid, which was used to form your ester. So you know that your name is going to start with ethyl, because the first part of the name describes the number of carbons that were in the alcohol that was used to form this ester. So it's ethyl, and once we have eliminated the 2 from ethyl, we've got 6. We've got 6 carbons left. And if we go back up quickly to the prefixes table that I got here, 6 has got a prefix of hex. So it means the final part of your name is start with hex, right? And you already know that the suffix, if you studied your functional group names, you know that the suffix for a for an ester is anoate. Ethyl hexanoate. So that's the answer for 2.4. Okay? And then 2.5 says, write down the structural formula of the organic acid X. So organic acid X is going to be your carboxylic acid. And all you have to do is write down the structural formula for it. So once again, you're trying to basically find the basic functional group, unit, or structure. You go to carboxylic acid, and this is your functional group that you're working with here. Okay? This is your functional group. So this has to appear on your structural formula. Okay? And as we already discussed, the ethyl, two of your carbons belong to your alcohol. So the rest of the carbons have to belong to your carboxylic acid, which means that your carboxylic acid had 6 carbons. Okay? So now we draw a chain that has got 6 carbons on it with the functional group that I just showed you at the top. Okay? And that's basically going to look something like this. Let me just make some more space. And that's going to look like this. We're going to go 1, 2, 3, 4, 5, 6, because we know that the hex, the prefix of hex means 6, and that belonged to the carboxylic acid because the ethyl or the other two came from the alcohol, ethanol. And now we just draw on the functional group that I showed you. It's going to have an OH and a double bonded oxygen because this is the functional group of a carboxylic acid. And now you just fill in your H's. H, 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 H. Here you've got to be careful, or start being careful. Remember, there can only be 4 bonds around one carbon. So 1, 2, 3, 4, and you're done. You fill in these with H's. Don't leave them empty when you draw it. I don't know how strict your markers will be in terms of giving you marks if you leave them open. And also, please try to draw it more neatly than I have here. But that's your answer for 2.5. Okay, cool, perfect. Let's move on. I just wanna. So I was moving all the way back at the top, up to the top to show you this, and I've actually left it here. Oh well. Okay. Question 3. So, question 3 says that the boiling points of different organic compounds are given below. And question 3.1 is to define boiling point. So what is boiling point? Once again, I'm going to reiterate that you have an official list. You should have an official list of definitions, and you need to study them word for word. Okay, your markers might not be so forgiving at the end of the year, and it needs to be basically exactly what's on the memo because they give you an official document, okay? But I'm going to read it to you anyway. And it says that the boiling point is defined as the temperature at which the vapor pressure of a substance equals atmospheric pressure. One more time, the temperature at which the vapor pressure of a substance equals atmospheric pressure. Okay, that's not something you can just guess. You have to know it, which is again why I say chemistry, the more you study, the better you do. Okay, 3.2, write down the 3.2.1, the name of the functional group of these compounds. So maybe I can just bring this back down here quickly to have a look. So we're looking for a C double bonded O OH group. Okay, I can tell it's a double bonded O because there isn't another H bonded to this carbon, which means that some of its bonds have to be used up on the oxygen. Okay, and it's basically the functional group we were just looking at. It's a carboxylic acid. Okay, it's got a double bonded oxygen and an OH group, and you can see that from the end of it here, the end of the formula here, COOH. Okay, now they say 3.2.2, give the IUPAC name of compound C. Okay, so again, you need to study your prefixes, you need to study your suffixes, so you know that the suffix for a carboxylic acid is oic acid. So we go and we say, okay, well, how many carbons are there? There's 1, 2, 3. And if we go back up to our prefixes, you'll see that the prefix for 3 is prop. Okay, and so that's your answer, propanoic acid. Because what is the end of it is oic acid. And our prefix is prop because there are 3 carbons in this one. So your answer there is propanoic acid. Propanoic acid. Okay? Then of the functional isomer B. Okay? So remember, an isomer is it's a compound that has got the same molecular formula, but something else about it is different. And a functional isomer specifically refers to a compound that has got the same molecular formula, but is a part of a different functional group. Okay? And so you're basically looking for something that has also got 2 O's in it and an H. So again, we come and we see, okay, well, which functional group also has got an O, 2 O's in it and an H? Okay, so we go and we have a look. We know it's not the carboxylic acid, but the only other option that doubles up on its oxygens, it's not an alkane, it's not an alkene, it's not an alkyne. It's not an alcohol, there's only one. It's not an ester, there's only ethers, sorry, it's not an ether, there's only one O. It's not an aldehyde, only one O. It's not a ketone. And so we are only left with one viable option, and that's an ester, because an ester is the only other functional group that has a double O. Okay, so we know that we're actually drawing an ester with the same molecular formula. The molecular formula for B being C2H4 O2. Okay, and if we build that into an ester, we know that it's only going to have 2 C's in it. One of the C's has to come from the carboxylic acid that makes it up, and one of it has to come from the alcohol. So we draw COC. And that's your final answer. That's your final answer for 3.2.3. Okay. 3.3. Which one of the compounds A, B, or C has the highest vapor pressure? Refer to the data in the table to give a reason for your answer. Okay. So the first thing I have to tell you here is that vapor pressure, I'm going to write it down now. Vapor pressure and boiling point are inversely proportional. What this means is that the lower vapor pressure is, the higher boiling point. The higher boiling point, the lower vapor pressure is. So basically, they move in opposite directions. As the one gets higher, the other one gets lower. That's what inversely proportional means. Okay, so when they're asking you to find the compound that has the highest vapor pressure, you have to have a look at the boiling points and decide from there. And because you know vapor pressure and boiling point are inversely proportional, you have to choose the compound with the lowest boiling point, because the one with the lowest boiling point is going to have the highest vapor pressure. Okay, so our answer for this one is A. And our reason is because boiling point and vapor pressure are inversely proportional. Okay, so it means that the compound with the lowest boiling point will have the highest vapor pressure. Okay, remember, just to quickly recap the definition of vapor pressure is the pressure exerted by a gas that is in equilibrium with its solid or liquid at a fixed temperature in a closed system. Okay, I'm not really going to go much more into detail there. I think that we can move on. Okay. Next, question 3.4. The boiling point of compound B is now compared with that of compound X. Okay. So 3.4.1 says, besides the conditions used to determine boiling points, give a reason why this is a fair comparison. Okay. There will only really be a few reasons why comparing certain compounds will be fair. Okay. Either they are in the same functional group, because it's fair to compare compounds that are in the same functional group, okay? Or another example will be that they have the same molecular mass. If you see a question like this and you see that they're in different functional groups, that's immediately a red flag for you, because generally the questions will steer clear of putting different functional groups in. It does complicate things a little bit. But if they are in different functional groups, what's positive is that it should immediately be a thought to yourself that maybe they have the same molecular mass. So what this means is that you're going to go to your periodic table and you're going to do the same kind of molecular mass calculations that I did earlier using the relative atomic mass that is available on the periodic table. So you'll say the relative atomic mass on the periodic table for carbon is 12. So you'll say 12 plus 1 for hydrogen, but there's 3 of them. So 1 times 3 plus another 12 plus 16, because that's the relative atomic mass for oxygen is 16, plus another 16 plus 1. And that's going to give you a total of grams per mole, a molecular mass in grams per mole. And then you'll do the exact same thing with the bottom one. And then if they have the same molecular mass, if that grams per mole value that you get from calculating off of the periodic table is the same, it means that it's fair to compare them. Okay, so that should be the first one you look at when you see that the functional groups are different, or it's not something obvious like chain length. But even then, it should still be in the same functional group. If they're wanting you to make comments on the boiling points of carbon chains and the carbon chains are different lengths, they should still probably be in the same functional group to make the comparison fair. Okay, so just something to think about. 3.4.2, Is compound X a primary, secondary, or a tertiary alcohol? Give a reason for your answer. So I don't actually know if any of you know how to define a primary, secondary, or tertiary alcohol. So in case you don't, I've just included this little summary here. But basically, you can see that a primary alcohol, the OH group or the functional group of the alcohol, is only attached to one carbon. Okay, so your OH is attached to a carbon that's only attached to one other carbon. So here, primary alcohol, your COH carbon is attached to one carbon. Your secondary alcohol is going to be where your COH carbon is attached to two carbons. So you see, you've got your C attached to OH, and that C is attached to two other carbons, whereas this one is only attached to one on this side. Okay? And a tertiary alcohol is one where your COH group is attached to three other carbons. So that's what it means. It's here if you want to have a look at it, if you're confused. Can't really go into much more detail there. Hopefully that helped. So they want to know, is X a primary, secondary, or tertiary alcohol? And you can see that just from the molecular formula here that the OH is attached to a carbon that is bonded to literally only one other carbon. So that means that your compound X is in fact a primary alcohol. And your reason is because your COH group is only attached to one other carbon. Okay? I hope that's helpful. Now we move on to 3.4.3. So fully explain the difference between the boiling points by referring to the types of intermolecular forces that are present in each of these compounds. Okay, so this is for 4 marks. So if you are in any way unsure about your answer, anything, I would probably recommend that you write too much rather than too little. They're not just going to give you 4 marks. You can't just write 2 sentences and hope that they're going to give you 4 marks. So you need to be trying to make as many connections here as possible. Okay, so I'm going to go through the explanation with you, and let's just read the question again. It says, fully explain the difference between the boiling points of B and X by referring to the types of intermolecular forces that are present in each of these compounds. So let's have a look. So both compounds X and B have London forces, as well as dipole-dipole forces, as well as hydrogen bonding. Okay, so you know that hydrogen bonding is the strongest, and then it goes dipole-dipole, and then London forces are pretty much the weakest. But B and X have got all 3 types of those forces. Okay, and the reason they both have got hydrogen bonding, okay, is because they have an oxygen, or they have got an OH group there. An OH group is present, which means hydrogen bonding is present. Remember, it's got to be hydrogen, fluorine, oxygen, fluorine, all of those major ones that count or fall into your hydrogen bonding section, right? Okay, so compound X is propan 1-ol. It's an alcohol, but it only has one site for hydrogen bonding. Okay, it's only got one site where an oxygen and a hydrogen are bonded together. Okay, compound B, which is ethanoic acid, also known as a carboxylic acid, has 2 or more sites for hydrogen bonding. Okay, this means that the intermolecular forces in compound B, the ethanoic acid, are stronger than the intermolecular forces in compound X, also known as propan 1-ol or an alcohol. Okay, or you can say intermolecular forces in compound X are weaker than the intermolecular forces in compound B. Okay, more energy is needed to overcome or break the intermolecular forces in compound B and therefore it has got the stronger intermolecular forces. And that's pretty much it. So you basically have to have a combination of any of the things that I've just described, at least 4 of them, at least 4 of those points, in order for you to get all of your marks. Okay, so remember that B has got 2 oxygens. And wherever an oxygen can form some kind of force or intermolecular force with a hydrogen from another molecule, that is an opportunity for hydrogen bonding. So more O or H, more O, more F, so more oxygen, more fluoride or fluorine, those molecules are going to mean more opportunities for hydrogen bonding. I just want to double check quickly. Just give me a second. So hydrogen bonding occurs when there is an attractive force between a hydrogen atom that is covalently bonded to a very electronegative atom such as nitrogen, oxygen, or fluorine. Okay, so that's how you know. If you've got multiple oxygens, multiple nitrogens, multiple fluorines, or a combination of them, you know that there's more opportunity for hydrogen bonding to occur. Specifically, if there is bonding occurring between those 3 atoms and hydrogen. Okay, I don't think I can explain much more there. Hopefully that helped. Okay, last 2 questions, question 4 and question 5. Let's talk about question 4. So, 3 reactions of organic compounds from the same homologous series are shown below. Okay, guys, this is now moving into organic reactions, another section that you will not be able to answer a single question for if you do not study. Okay, unfortunately, I can only go through these answers with you. There's not much explaining that I can do outside of you actually physically going to sit down and memorize this stuff. You literally need to memorize it like a parrot. You need to what we call parrot learn it. You learn it so that it's super easy for you to repeat it to yourself in the exam. Okay, there's no logical way to answer these questions. You either know the answers or you don't. Okay? So 4.1.1 says define a homologous series. And the official definition for this is a series of organic compounds that can be described by the same general formula or functional group. One more time, a series of organic compounds that can be described by the same general formula or functional group. Okay? 4.1.2, name the type of reaction represented by I. Okay? So let's have a look what's happening. We start with butane, which is an alkane, okay? Our reactants, or one of the additional reactants is bromide, okay? And then what do we get? We get a haloalkane, because this is a halogen. So this is actually a process of halogenation. It means you're removing hydrogens from your alkane and you're replacing them with your bromide or your halogen, which is also known as halogenation because it means you're adding halogens to your alkane. Okay, and this is also known as substitution. It's a substitution halogenation reaction. Okay, and like I said, if you haven't gone over those reactions, you won't know what to do here. Okay, 4.1.3, write down the formula of the inorganic compound P. Okay, again, you're gonna have to learn what are the reactants in these reactions. what products are formed. You need to know all the products that are formed. You need to know the catalysts. You need to know the reaction conditions. Is heat needed? Is a specific type of catalyst needed? What reactants give me what products? Again, like heavy studying, heavy memorization to be able to do well in this section. Okay. And so again, if you studied, you know that one hydrogen is removed from your butane and it's substituted with one Br or bromine atom from your Br2, and that H that's now been removed forms a bond with the leftover Br, and so your product P is HBr. Okay. 4.1.4, give the structural formula of a positional isomer of 2-bromobutane. Okay? Structural formula of a positional isomer. So a positional isomer means it's got the same molecular formula, but your functional group is basically in a different position. Okay, so you can see in this one, your bromo was on the second carbon. This describes the position of your bromide atom, and it's telling you that it's on the second carbon. So all you have to do is just move it to a different carbon. Make sure make sure that the compound that you draw doesn't have bromide on the same carbon. So 1, 2, 3, 4. We've got 4 carbons. In the original, in the 2, this is what the original looks like. This is 2-bromobutane. It means that Br is on your second carbon, and the rest of it is like a normal alkane. It's just got H's. Okay? And so, like I said, an isomer is a compound that has got the same molecular formula, but something specific is different about it. And they're asking for a positional isomer, which means that whichever section of your compound or your carbon molecule makes this what it is. So this is a haloalkane. It's an alkane because there's only single bonds, but it's an alkane that has a halogen in it. It's got an imposter. It's not only made up of hydrogens, okay? So this is what is basically making your functional group here, this halogen. So positional isomer literally just means that you've put your functional group somewhere else. So literally all you have to do is change something small. Change the position of your functional group. So it becomes 1-bromobutane instead of 2-bromobutane. I hope that makes sense. I hope that helped. Okay, now we move on. 4.1.5, using molecular formulae, write down the balanced reaction for reaction 2, the balanced equation for reaction 2. Okay, so let's have a look at reaction 2. We're taking pentane, which is an alkane. We're exposing it to excess oxygen and heat, and it's giving us what? What is it going to give us? Okay, so again, something that you either know or you don't know. Chemistry is harsh like that, okay? But your cues here are excess oxygen and heat. Those should immediately be ringing alarm bells in your head. that this is what we call a combustion reaction. And what this means is that you are burning some kind of fuel. You're burning something you're burning it in oxygen. Because remember, fire needs oxygen to live. Like a fire will die if it doesn't have oxygen. So the excess oxygen and the heat tells you that it's a combustion reaction. And it makes sense that this is an alkane because alkanes are ideal fuels. They're good burning materials, okay? So your reaction should go something like this. Pentane, you know the general formula for an alkane is CnH2n plus 2. So you know you've got 5 carbons. So you know your formula for pentane is going to be C5H. 2 times 5 is 10 plus 2 is 12. C5H12 plus, they say excess oxygen. So you know you've got to put oxygen here, and you know that oxygen is a diatomic molecule, so you can't just put it as O, it has to be O2. And this gives you two products that you also, only if you've studied combustion reactions, you know that it's CO2 plus water. Okay, our only problem now is that this is not balanced. Okay, they specifically said they want a balanced equation. So now you've got to go and you've got to balance it. I just want to take a second to just fix this. Okay, so you need to balance it. I'm gonna take you through step by step. I feel like maybe most of you don't need me to do this because balancing is quite a big part of like chemistry right from grade 10. But I will show you how I balance equations anyway, just in case. Okay, so you say carbon, hydrogen, oxygen. Same thing on this side. Carbon, hydrogen, and oxygen. So balancing equations is exactly what it sounds like. You're trying to make sure that there's the same number of carbons on the left-hand side as they are on the right-hand side. The same with hydrogens. Are there the same number of hydrogens on the left-hand side as they are on the right-hand side? And the same with oxygen, okay? You're trying to make sure that the number of atoms is conserved because matter can't be created or destroyed, okay? So then you need to have the same amount. You can only form new bonds. You can't destroy or create atoms. So you have to have the same number on the left as you have on the right. So we say, okay, well, how many carbons do I have on this side? I have 5. Okay. And I say, well, how many hydrogens do I have on this side? 12. How many oxygens do I have on the side? 2. Carbon, I've got 1. Hydrogen, I've got 2. Oxygen, I've got 3. So you can see actually like none of my numbers are making sense right now. Okay. So the first thing I think we should do is I can kind of manipulate oxygen on this side without pretty much manipulating anything else. Okay. So I can make that a number that makes sense to me. That's where I can start. Or I can start on the other side of the equation. It's completely up to you. I don't know how you've been taught to manage these types of things. So let's see. I think I'm going to start on this side. You can see that here I've got 12 hydrogens, and on this side I've got 2 hydrogens. Now this is pretty simple to fix for me because all I have to do is multiply this side by 6. So actually, let me do this in a different color. If I multiply this side by 6, I can get 12 immediately and fix my hydrogens right off the bat. Okay. This does, however, implicate my number of oxygens. So now I've got 6 oxygens plus the 2 over here. So this number changes to 8. Okay. So now my carbons and my oxygens aren't looking so great. Okay. But it's also pretty easy for me to fix this one. I can literally just multiply this side by 5. So I can make this side look exactly like this side. So this becomes 5. Okay. And now I say to myself, okay, but that's also messing with my oxygen again now. So I say 5 times 2 is 10 plus 6. I've got 16 oxygens now. I've got 16 oxygens on this side, and I only have 2 on this side. But now magically, this is also pretty easy for me to fix, because how do I make 16? What can I multiply by 2 to give me 16? That one's pretty simple too. I can just multiply that by 8. And just like that, you have a balanced equation. So, yeah, I should have said at the beginning, if you're okay with balancing, you should probably skip this part of the video. But either way, hopefully that was helpful. Okay, so that was 4.1.5. Let's move on now to 4.1.6. So it says reaction 3 is an example of a cracking reaction. Define a cracking reaction. Okay, so here it says cracking is the chemical process in which longer hydrocarbon chains or longer chain alkanes are broken down into shorter, more useful hydrocarbons or molecule chains, such as alkanes and alkenes. Okay, one more time. The chemical process, so cracking is the chemical process in which longer chain hydrocarbons or longer chain alkanes are broken down to shorter or more useful hydrocarbons and molecules, such as alkanes and alkenes. Okay, hopefully that's okay. 4.1.7, give the structural formula of organic compound Q. Okay, once again, more studying. Cracking is a type of reaction you need to go study, okay, so that you know what the products will be. So here we've got hexane. That means this prefix means 6. You can see that an alkene has been formed that has used up 2 of your carbons, and that means that you've got 4 carbons left. And that will form an alkane. Alkenes and alkanes are usually the products of a cracking reaction, but you can go and do some more study work on that, and it will tell you how to identify and also draw the main and minor products, the major and the minor products of these types of reactions. Okay, so your major products here will probably be this alkene, and your minor products will be the leftover alkane, which is literally pretty simple to draw. Like I said, you've used 2 of the carbons from your original alkane. Now you just use what's left. So 4.1.7 is 1, 2, 3, 4. Yeah, and that's it. That's 4.1.7. That's your organic compound Q. Like I said, just go do some more reading on these reactions. It's very much study work. Okay, let's get rid of this. So now we have a look at study the flow diagram below. 4.2.1, write down the IUPAC name of compound R. Okay, so you're starting with a haloalkane, okay? And your haloalkane is undergoing hydrolysis, okay, which means that water is being added. Okay, this kind of implies that remember, hydrolysis is the addition of an OH group to an alkane, or a haloalkane for that matter. So this is probably a substitution reaction, and you're going to have to get rid of one of your bromos and replace, or you're getting rid of both of your bromos and you're replacing it with the OH and the H from your H2O, your H2O molecule during the hydrolysis reaction. So this means that your compound R is going to be butan-2-ol. So this is basically what the reaction is going to look like. You're going to have bromobutane, so 1, 2, 3, 4. So it's saying 2 bromobutane, so it means that the bromo is going here, and the rest of them are H's, because it doesn't say that there's 2, otherwise it would give you 2 numbers, like 2, 2, dibromo, and the di would tell you that there was more than one of them, but there's only one. So this is what it looks like. Remember, we're answering 4.2.1. So this is what it looks like. Now, it's a substitution reaction, hydrolysis, so we add H2O. So what happens? Br gets split from our alkane. H2O splits up into H positive and OH negative. This OH then moves into this position, and this bromo bonds with the leftover hydrogen. So basically what you're left with is and that's what you're left with. Okay, so this is compound R, which means that compound R, the IUPAC name for is 1, 2, 3, 4 carbons, which is bute, and our OH group is on our second carbon, so the name of it is butan-2-ol, because the functional group is alcohol. Okay, like I said, there's not much more I can do to explain these. This is very much study work. I know it's probably getting annoying me saying that now. My apologies. Okay, let's keep going. Let's do 4.2.2. Compound R reacts in the presence of concentrated phosphoric acid to form an alkene. Write down the structural formula of the major product in this reaction. Okay, so this is going to be an elimination reaction because you're turning something that only has single bonds into something that has double bonds. So it means that you're not replacing anything. You're not swapping anything to keep it the same, because that would be substitution. You're not adding anything to change it into a single bond functional group, but you are taking something away. You're removing something so that double bonds can be formed. Okay? And so your major product here is going to just be removing the OH. So you're going to start with your butan 2-ol. This is the butan 2-ol that we just named from 4.2.1. It's an elimination reaction, which means things are being removed to form a double bond. And you're basically going to be removing an OH and an H. Okay? And for this section, if you just give me a second, this is an elimination dehydration reaction that we're talking about here. Okay, so dehydration means that you're removing water, you're removing a water molecule from your alcohol. And when we do this, we remove the OH, but there is a rule to deciding where you remove the hydrogen from. Okay, because you have to remove an OH from one and a hydrogen from the other. So how do I know if I put the double bond between this carbon and this carbon, or I put the double bond between this carbon and this carbon? Because you can't remove two things from the same carbon. You can't remove the OH and the H from this carbon. And so the rule that basically guides you is called Zaitsev's rule. And Zaitsev's rule says that you remove the hydrogen from the carbon with the fewest hydrogens. So it's got to be one of the carbons that's bonded to the carbon that has the OH group. Otherwise, no double bond will be able to form. So it's got to be either this carbon or this carbon. And the rule says that you remove it from the carbon that has the least amount of hydrogens. We call it the rich get richer and the poor get poorer rule, or the poor get poorer, because you're stealing a hydrogen from the carbon that already doesn't have that many hydrogens. So according to this rule, we remove the hydrogen from here. And it becomes And the reason you know that this is going to be the major product, because this is your major product now, this is the answer, is because the major product is going to be the one that follows Zaitsev's rule. Okay, if they ask for the minor product, then it's going to be the version of the molecule that doesn't follow Zaitsev's rule. So that will be removing a hydrogen from this carbon instead of this one. But your major product is going to be the one that follows Zaitsev's rule, where you take the oxygen or you take the hydrogen from the carbon that has the least number of hydrogens. Okay. Okay, now we move on to question 5. Last question for this video. Okay. Let's see. So question 5 says that the reaction of zinc and excess dilute chloric acid is used to investigate factors that affect reaction rate. The balanced equation for this reaction is blah, blah, blah. You see it there on the screen. The reaction conditions used and the results obtained for each experiment are summarized in the table below. Okay, so you can take a minute, have a look, and then 5.1. Experiment 1 and 5 are compared. Write down the independent variable. So what are we changing? What's different? So remember, the independent variable is the variable that goes on your x-axis, and it is the variable that is manipulated by you, the researcher, the scientist, the investigator. Okay? It's not what you're trying to observe. It is what have you changed? What variable are you playing around with to basically see what its effect is on some kind of outcome? So here's experiment 1, concentration of 2 moles per decimeter cubed of HCl. Same for 5. Remember, if the experiments you change one variable, the rest of them have to be constant. So we need to make sure that the rest of them are the same. Volume, the same. Volume, the same. State of division of zinc, powder, right? That can't be different because otherwise that could be affecting it. So everything's the same so far. And now, number 1 has a temperature of 25 and number 5 has a temperature of 35. Okay? So what is our independent variable in 5.1? It's got to be the thing that we changed, right? So it's got to be temperature. Temperature is your independent variable here. It's the one that you have changed. It's the one you have manipulated to see what the outcome will be. You want to see how will that change in temperature affect my observable results. Okay? 5.2, define reaction rate. So reaction rate is change in concentration of products or reactants per unit time. It's quite a simple one. I'll do it one more time. It's the change in concentration of products or reactants per unit time. Okay? 5.3, write down the value of X in experiment 4. So here's experiment 4. They pretty much haven't given us any additional information. Okay? So now what you got to do is you got to go and compare. You got to go compare number 4 to the rest. We can't compare it to 5 because the concentration is different. Our concentration of HCl is different. We can't compare it to 3 because our concentration is different. Can we compare it to 2? Yes, our concentration is the same. Okay, let's see. Is our state of division the same? Yes, it is. Is our temperature the same? Yes, okay. The only thing that's different is volume. Okay, and in this case, volume doesn't really mean anything. Okay, the concentration is the most important factor here. It basically means that the same amount of HCl is going into each of these reaction vessels. It's just going in with a different quantity of solution. But the concentration is the same, which is the key thing here. And everything else is the same. So you know that changing the volume but delivering the same concentration probably means that I can assume that the reaction time for experiment 2 was identical to the reaction time for experiment 4. And so I said that X was equal to 14 minutes. Okay? Now we move on to 5.4. The Maxwell-Boltzmann energy distribution curves for particles in each of experiments 1, 3, and 5 are shown below. Identify the graph A or B or C that represents the following. So 5.4.1, we're looking for experiment 3, and 5.4.2, we're looking for experiment 5. Okay, so let's go compare them quickly. Get rid of these. So these are the ones we're focusing on. We're focusing on 1, 3, and 5. So let's just quickly compare. 1 has got a concentration of 2 3 has a concentration of 5, 5 has a concentration of 2. They have the exact same volumes, they're all in powder form, and only one of them is at a different temperature. So I'm going to go and I'm going to circle the things that make them different. The temperature of 5 makes it different, and the concentration of 3 makes it different. Okay, so experiment 3. Which one of these graphs is going to be experiment 3? Okay, well, we've already determined that the thing that makes experiment 3 stand out is its concentration of HCl. Okay, and concentration is directly proportional to the amount of substance that I have, otherwise known as the number of molecules. So experiment 3 is obviously going to be the graph that shows the highest number of molecules on my graph. Which one peaks? Which one has the most molecules? And that's going to be B. So experiment 3 is B because it has the highest concentration, which is synonymous with an increased amount of reactant and an increased number of molecules. Okay, so experiment 3 is graph B because it has a higher concentration, which is directly proportional to an increased number of molecules. Okay. Let me just give me a second. So graph B, because experiment 3, yes, has the highest concentration. Okay, perfect. Then we want to see experiment 5. Now, which one is experiment 5? So you can see the key thing that makes experiment 5 different is its increased temperature. Okay, and temperature is directly proportional to kinetic energy. They're basically the same thing. Okay, if I'm increasing temperature, I'm increasing kinetic energy. If I am increasing the heat or energy, remember, heat is a type of energy, especially when it comes to chemistry and particles. So if I'm increasing the temperature, I'm making sure that more of my molecules have energy. They've got an increased amount of energy. So we have to choose. An increasing temperature will mean that more of your molecules, more of the area of your graph is on the other side of your activation energy. You can see your graph here says activation energy, right? So more of your graph, when you increase temperature, you shift more of your graph over to the right-hand side of your EA line. It means that you are increasing the number of molecules that have a kinetic energy that is either equal to or higher than your EA. And your EA is the amount of energy needed for effective collisions and basically a chemical reaction to occur. So based on that alone, you know that experiment 5 has to be graph C, because you can see it's the graph that has got the most area on the right-hand side of your activation energy. Okay? Increasing kinetic energy, increasing temperature increases the kinetic energy of the system. Increasing the kinetic energy available to be absorbed by molecules means more of your molecules will have a sufficient amount of energy to participate in the reaction. And the only graph that shows a significant portion of its area on the right-hand side of this activation energy line is graph C. So it has to be graph C. Okay. 5.5, a sixth experiment is now conducted using a catalyst and the same reaction conditions as for experiment 1. So it's got a concentration of 2, 200 volume, powder form, 25 degrees Celsius. So everything's the same except for now we are adding a catalyst, okay? And the question is, what is the function of a catalyst in an experiment? Okay. And the function of a catalyst is that it speeds up your reaction or increases your reaction rate. Okay. It lowers your activation energy. Okay. It makes it possible for more of your molecules to participate in the reaction and increases reaction rate. That's the answer. Okay. 5.5.2, how will the heat of the reaction in experiment 6 compare to that in experiment 1? Choose from greater than, equal to, or less than. And the answer is equal to. Adding a catalyst will not change the heat of the reaction. It will not change the temperature of the reaction vessel. It will not change anything except for your reaction rate. A catalyst uses other chemical mechanisms to bring about an increased reaction rate. A catalyst does not increase the heat of the reaction. So your answer here is equal to. Okay? And then our last question for today is calculate the average rate of reaction in moles per minute with respect to zinc for experiment 2 if 1.5 grams of zinc is used. Okay, so you can tell reaction rate equals moles. You can see from the unit of something what you have to do in order to get it. If they're saying that the unit for your reaction rate is moles per minute, remember this to the -1 insinuates that it was at the bottom of your denominator. It was in your denominator position of your fraction. So they're basically saying to calculate this reaction rate, put moles over minutes. Okay? So we say our only issue here is if we go and we use the exact same reaction conditions as experiment 2, it says that it took 14 minutes. So you know that your minutes are 14, but you still have to calculate your moles, and they've given you mass. And you know that you can convert mass to moles if you know the identity of your atom, which you do. So we say the formula for converting mass to moles is number of moles is equal to mass over molar mass, small m over big M. So that's going to be equal to 1.5 grams. Luckily, that grams is our SI unit for chemistry, so we don't have to convert it. And our molar mass, you need to go to your, or the molecular mass, you need to go to your periodic table, and you need to look for the approximate relative atomic mass of zinc. And you can see from the equation that it's not 2, it's not Zn2 subscript 2, it's just zinc. So you only have to write it in once. And the approximate relative atomic mass for zinc from your periodic table is 65, which means your number of moles is equal to, you plug that into your calculator, you say 1.5 divided by 65 gives you 0.023 moles. So now we can go and we can plug that value into here, 0.023, because remember it's moles over minutes. You divide those two, so you take your 0.023, you divide it by 14, and what are you left with? You're left with a reaction rate of 0.0016 moles per minute. And that's your answer. Okay. And that's it for today. I will carry on with the next video. I'll carry on with questions 6 to 10 in the next video. Thanks for watching.